So for our next section, we're going to take a look at some handy high-level utility functions that Pandas data frames either ship with or in ways in which they can be combined with built-in Python functions and NumPy functions. So we're sort of done accessing the data and indexing. We've covered all of that. This information is available here to you in the slides, but I'm going to continue running through the notebook live so that we get a more interactive feel for this. So let's imagine that we pull out from our elections data set just a percentage of the winners. So this is going to be a series that is purely a series of numerical values. This is basically as close as you're going to get to a standard NumPy array. This is just a series of numbers, but it does have an index, which NumPy arrays don't have, right? That is the one distinction. But because it is very much like a simple NumPy array, standard NumPy operations work on it, so you can compute things like the maximum, you can compute things like the mean, or you can compute more complex more complex algebraic operations. Say that you wanted to compute a mean square error around either the mean or a different value, then you can do so with this expression, right? You have a constant, and then you apply the array. You treat winners, even though it is a Pandas series, as if it was a NumPy array, which means you can compute the element-wise differences, square them, and take the mean, which will do all the summing and averaging for you. So these things behave very much like NumPy arrays, and that's part of the big power of Pandas. Now, they behave so much like a NumPy array that you can do things that are somewhat absurd. This is an example of saying, let me grab the data frame, a data frame that has the columns, percentage, and year. These are purely numerical columns. And now let me add 3 to it. What does it mean to take a data frame and add 3 to it? Well, in this case, you're adding 3 to the year and adding 3 to the percentage. Semantically, this doesn't make any sense on this data, but we want to illustrate that mathematically, Pandas allows you to do these kinds of operations. So if you have a data frame that is purely numerical data, you can basically both do all of these data-driven operations and querying and whatnot, but you can also treat it like a matrix, basically, like a NumPy array, and operate on it, which taking an array and adding 3 to it is a perfectly sensible thing to do on an array. So in this case, data-wise, this is, from the perspective of the domain of the data, this doesn't make sense, but it's a valid operation. Now, there are a set of really useful methods that you should take a look at. Let's load this other data set, the mottos. Let's take a look at what the mottos data set is. The mottos data set is a CSV file that has the state mottos, the original of the state motto, translations, the original language, the date they were adopted. You can see that in this case, the date is not a numerical column, because it actually, some of the dates are numbers for years, but some of them are actually specific dates. So if we load this with our handy read CSV function, this is what the data frame looks like in Pandas. So the size attribute gives us the complete size. Basically how many cells are there in this file, if you will? How many cells are there in this table? This is the number of rows times the number of columns. So it only has, it has 250, not 200. So this is a small typo here that we will correct live. So this is a table that has 250 total entries. What is the shape of this? Well, shape is a method that NumPy arrays have, and Python and Pandas data frames have it too. It gives you the number of rows and the number of columns. So in this case, you know that they have 50 rows and 5 columns. The 5 columns are right here: state, motto, translation, language, and date adopted. We had already looked at that. The fact that we have 50 rows, since we're looking at state data, tells us that we probably have all of the states, but we don't have other territories like, say, Guam or Puerto Rico or Washington, D.C. that are not state. Now, data frames have a handy kind of summary method called describe, which gives you a high-level summary of some of the properties of the data. So for each of the columns, it will try to compute a few statistics: the count of how many non-empty values are there, how many unique values are there, which is the maximum value, which is the top value, and this may make more sense or not, depending on whether the data is what the type of the data is, and the frequency of these occurrences. So, for example, we see that the most common language here, if we look at language, the most frequent language is Latin, and it happens in 23 different states. So we can see here that Latin is actually a very, very common. It appears many times. English comes after, and there are actually a few other occurrences. There's a couple of occurrences of other languages, but Latin and English are the top ones, as you would sort of expect. But there are also some interesting things. We have 50 unique mottos, but we only have 30 translations. Why would that be the case? Well, if we look at the translations, it turns out, and it's because the top translation is actually dash. So there are mottos that are untranslated because they're in English to begin with, and so those that are in English to begin with are untranslated, and that is why we have a mismatch in these. So this type of high-level summary is the kind of thing that whenever you load a new data set, looking at head, looking at its size and shape, taking a peek with head and tail, and you should look at both to make sure that the data makes kind of sense on both ends. Sometimes you could have a corrupted file, and the data at the bottom, for example, is very weird or has strange things. And looking at calling describe on your data gives you a sense of what's in there. Later we'll do a lot more around exploratory data analysis, which is kind of this sense of getting very closely acquainted with your data. But this is sort of the beginning of that with Pandas data frames. Now, we've talked a lot about the index, right? This special column here that appears over here. We've talked a lot about the index, and so this is a case where the index by default, as we loaded it, the index by default is an integer. Now let's actually ask for this motto's data set to be indexed by states instead. And the reason why I want to load it that way is because it kind of makes sense if I'm thinking of data about the mottos of all the states to use the state as my index. So if I do that instead, this is what the data frame looks like now. And interestingly, I want to point out something that happens in here. The size actually changes. So I should correct that back. When I fixed it, I had forgotten that the original loading was with the motto, and this is why it changes. The size changes to 200. But this illustrates an important point. The data is the same. The raw data in the CSV file hasn't changed, but we're representing it in two different ways. In one case, we are loading the state data as part of the data set, whereas in the other case, we're saying the state data is the separate bookkeeping object called the index, and the data itself is only this part. And so how the size of the data set in this case changes because one column is pulled out of the data by making it into an index and is turned into what we sometimes refer to as metadata. It's data that is used to access the other data, but we're pulling it aside. And so if you think what will happen when I rerun this cell and I recompute the shape, I will have, instead of 50 by 5, I will have 50 by 4. I will have one less column. Now this isn't, now the state column is going to disappear, obviously. But the reason why you wanted to see this is because now we see that the index is a special type of object that we can access that looks kind of vaguely like a series but with no more data in it, and it has a name, right? You can have a name and you can actually access that object. So it turns out that indices have a lot of stuff in them. So if I hit tab after the dot, you can see that index objects have quite a bit of stuff in them. They really have a lot of stuff. And for example, they have a name. So this is the name object. We won't spend time digging into all of the properties of indices, but this is what happens since the index was made from a column that had data in it and a named column. Then Pandas will preserve that information for you. as we can see here, this was the end. Now columns, this part of the data frame, if you think of it as a table, well, there also actually is an index in there. So you can actually access the columns object of the data frame, and it is itself an index. It is an index that itself by default doesn't have name, but you can actually name it. So the columns.name is nothing. But if I say columns.name equals properties, for example, now you see, this is kind of an extreme example where now I have named the column index as properties, and we still have the row index that was named state, and so both indices can have each their own name. We by default typically the column index doesn't have a name, so this is what it would look like, kind of in the more standard case. But you can, if you want, if it makes sense for your analysis, you can name both of your indices. Now, a very, very useful method of Pandas data frames that at least we want to mention today is the sort values method, which allows you to sort a data frame based on a specific column. It's one of the handiest things you do if you've used any spreadsheet software, Excel, Google Sheets, etc. You've probably done that kind of thing over and over. You take a spreadsheet and you say, oh, I want to sort it by this thing, and you do that by kind of clicking around. In Pandas, you can do so by using the sort values method. So if I want to sort the election data from lowest to largest percentage of the vote, then I can say sort values. It doesn't modify it in place, as we said before. Most of these things return new data frames, though they do have an in-place method, an in-place argument if you want, if you do want to modify it. And so this lets me sort my election data by vote. You can see all of the arguments that the sort values method takes, which are quite a few. In particular, you can choose a sorting algorithm, but importantly, you can choose easily whether to sort in ascending or descending order. So if I want to sort in descending order, I type ascending equals. And by the way, in Jupyter, if I start typing actually keyword arguments and I hit tab, Jupyter will complete for me. So the default of this is true, but if I say false, now I get a reverse sort in descending order, where now they're sorted from largest to smallest. But again, remember that these always return new values that leave the original unchanged. So this was the example using ascending equals false, and finally, we can use the same sort values can be used also in series. So if we grab a single series, the same exact. Now in this case, you don't pass an argument because there's only one column already to begin with. So, but you can sort a series in this, and it accepts the same exact. And you can sort it in reverse order, all the same. So the same exact information applies. So let's take a pause here so that you can play with these ideas a little bit and take a look at the quick checks, and then we'll wrap up with the remainder of the lecture.